Hello, everyone. Hi, everyone. My name is Benjie. I've been working on turning off my notifications. I've been working on a new execution engine for GraphQL called Graphile. It enables greater efficiency across your entire backend stack by leveraging the declarative nature of GraphQL to give your business logic a better understanding of everything it needs to do. It's backwards compatible, so you can use it within your existing schemas, adopting it incrementally, and it's finally ready for people to try. I've released the source code onto GitHub under the MIT license, and version 0.1 just went onto NPM this morning. You can find the documentation at graphile.org, and there's a few decisions and finishing touches that need to be made before the big 1.0 release, at which point I plan for there to be a specification so that it can be implemented in any GraphQL service. If you're interested in the future of this technology, please get involved in the working group at github.com/graphile/WG. Thanks for coming to my talk. Okay, so maybe conference talk shouldn't be quite that efficient. Let's start again. So let's have a look at how bowling pins are handled in The Simpsons. This is from season 6, episode 13, about 9 minutes into the episode. You can see how the old pins are discarded, then an entire log is chopped down to a single skittle, which is then painted, coated, heated, painted again, inspected, before then being placed as just one of the pins in a rack of 10. The absurdity of this scene struck me at the time and has stuck in my head ever since I watched it back in 1995. The inefficiency in this is ridiculous, right? Ridiculous. That would be like habitually selecting everything from a table and then only using one of the attributes. Let me introduce myself. My name's Benjie. I'm a fan of VR. I'm one of the members of the GraphQL Technical Steering Committee, and I'm a significant contributor to the GraphQL specification. You can find me on GitHub or Discord, where I help and offer guidance to people who are getting involved with the spec itself. I'm also one of the people that helps the GraphQL working groups to continue progressing by doing the chores. I help to file the notes and the action items. I sync the videos onto YouTube so that you all can watch them. And I help to manage the agendas. Now, I recently reread a blog post that Andrew Ingram wrote back in 2017 called Optimizing Your GraphQL Request Waterfalls. In it, he uses this example of an upcoming events page for a user, and the displayed query is used to get all of the data for this web page. He then goes on to show a few different ways of executing this query. So to start with, we have the simple but slow approach, where each field's resolver is responsible for getting its own data independently, and that results in 47 requests to the backend. Now, we all know about this. This is the infamous N+1 problem, and it's easily solved in version 2 by batching the nodes. This uses data loader in the most common way to batch fetch records by their individual IDs, which results in a reduction down to just 16 requests to our backend. In version 3, Andy uses a technique where he also batches those connection fields. So though not all data sources actually support this style of batching, especially when you're adding limits and maybe conditions, Andy notes that batching them inside of GraphQL means that your next layer of resolvers will all be synchronized, so that next layer of batching will be more efficient, and that reduces the number of requests down to just 8. From our original 47, that's a pretty good saving, right? But still, we've got to be able to make it more efficient than this, right? Let's forget about GraphQL for a minute, controversial, and imagine that you want to build a REST endpoint. Your REST endpoint wants to return the same data as you would return for a GraphQL query like this one. Let's imagine that we're getting the data from a database and we're using a ORM, which will be active record, the ORM that's used in Ruby on Rails. You might use this kind of approach. First thing you want to do is load your user, and you're just going to get their name and their username. Then you want to load the upcoming events for that user. So you're going to load the events, then get your attendance to that event, along with the details of the venue that you'll be attending, and then select from that the attributes that you're interested in. And finally, we would find the list of attendees of these events, and with a little help from our friend Stack Overflow, we can then limit them to just the first 4 attendees who are our friends. And finally, select their avatars. Now, you could likely achieve something like this in most ORMs in almost any programming language. So solving this specific GraphQL query with simple code has only required 3 round trips to our database. Why 8 then in GraphQL? We call this problem underfetching. It's where you have to keep going back to your data source again and again to get the next bit of data because you didn't ask for enough of it up front. Though GraphQL seems to solve the over and underfetching problems on the client side, it seems to make them worse on the server side. Another thing, when we fetched the friends that were attending the event, all we needed was their avatars. And yet, because our resolvers don't know that this is all we need, we end up loading the entire user objects for all of these things, only to throw most of it away. No need for username, for their multi-paragraph, highly crafted bio, or for their email or anything else on that user object. Overfetching and underfetching. This is not efficient. Having seen so many different workarounds for this problem over the past few years, I can't help feeling that GraphQL's execution model is wrong for most servers. Please don't tweet this out of context. GraphQL is amazing. It's an absolute delight on the front end. And it's a declarative language. The client specifies everything it's going to need up front. But the resolver-based execution model obfuscates this knowledge. And that seems like so much wasted potential. So, how do I reconcile this with my belief that GraphQL is amazing? Well, that's easy. In 2017, Lee Byron helpfully added this clarification to the spec. Conformance requirements expressed as algorithms, like the execution algorithm, can be fulfilled by an implementation of this spec in any way, so long as the perceived result is equivalent. So, resolvers define the observable behavior for GraphQL execution, behavior that we rely on for things like normalized caching. But our servers are free to actually implement this outcome however they want. Back in 2020, I set out to design a system that would leverage the declarative nature of GraphQL to execute queries on the server as efficiently as possible. And though it was clear to me that the solution would involve a degree of query planning, I wanted to ensure that developers would be able to use it without a degree in sorcery. And I think I've done it. I'm here today to say, step aside, resolvers. There's a new way to execute GraphQL. This new technology is called Graphast, and it's a cutting-edge planning and execution engine for GraphQL. Graphast, like GraphQL, is not specific to any particular technology stack, business logic, shape, or data storage layer. It doesn't care if you're using relational databases, document stores, ORMs, HTTP APIs, file systems, or carrier pigeons. So, let's talk about how it works. Graphast's job is to look at your incoming GraphQL request and the description of your business logic, and to build or draft an execution and output plan. It can then, with the help of your business logic descriptions, optimize and streamline this plan. This may involve changing the shape of execution significantly from the shape that the GraphQL request would imply, enabling the system to satisfy the requirements of the request in the most efficient manner. Now, once this planning phase is complete, Graphast will execute this highly optimized execution plan, and it will feed the results into the output plan, which will prepare the results to be sent to the user as a regular GraphQL response. Now, we don't need to do this planning and optimization on every request. If another request comes in using the same GraphQL document but different variables, then we can just retrieve the existing plan and jump straight to our highly optimized execution. Soon, we'll be writing a specification for Graphast so that this exciting planning and execution model can be brought to any programming language. But since the initial implementation is in TypeScript, let's have a look at what it means for JavaScript schemas. In traditional GraphQL execution, each field has a resolver that tells the system how to fetch the data, or that actually fetches the data for that field. Now, don't worry about the specific code. We're just generally looking at the shape. In GraphFast, a plan resolver serves a similar purpose, but rather than actually getting the data, it's responsible for describing the steps required to get the data. As you can see, the code on both sides is relatively similar. GraphFast plan resolvers are designed to be written by humans. Let's take a look at planning a simple GraphQL query. Just like in traditional GraphQL, we go through the fields on a layer-by-layer basis, starting in this case with the current user field. Here's the plan resolver for that. The first thing that we call is this context function, and that is going to give us a step that represents the GraphQL context. Next, we want to access the current user ID property, which will give us a step that represents this access. Note the arrow shows that at execution time, this new step will be dependent on the results of the previous step. And finally, we call user by ID, which will give us a step representing loading this single user. Now, this final step represents the result of the current user ID field. So when we plan the next layer of fields, this result is then used as the input, similar to the parent object in traditional resolvers. As we continue to plan the query in this way, we build up our draft plan step by step. This plan can evolve significantly from the first draft before it comes time to actually execute it. But before we can talk about that, I'd better tell you what a step actually is. A step is the basic building block of our execution plan. At execution time, a step is very similar to data loader. A list of inputs is mapped to a list of outputs via batch execution. But at planning time, steps can interact with each other, determining exactly what needs to be done and transforming the plan such that the execution will be as efficient as possible. Out of the box, GraphFast comes with a number of optimized steps that you can use to build your plan resolvers, like the ones that we saw earlier. For now, let's focus on this load one step. This step is similar to data loader, to data loader's load method. It's responsible for batch loading individual records from your business logic. In fact, load one is so similar to data loader's load method that you can use your existing data loader callbacks with it. Whereas in a traditional resolver, you'd probably get the loader from the GraphQL context and call the load method passing in the ID. In a GraphFast plan resolver, you'd call load one, passing the data loader callback directly along with a step that represents the ID. This also means that unlike in traditional GraphQL, where you'd have to add all of your data loaders to each GraphQL context, there's no need to do this in GraphFast. So moving from data loaders in resolvers to load one in plan resolvers is relatively straightforward. And because everything is batch processed in GraphFast, achieving Andy's version 3 schema happens almost automatically. But if we go back to Andy's post, he's been a little bit crafty. Andy's mastery over the arcane topic of look-ahead allows him to transform the version 3 waterfall into a more compressed version 4 waterfall as follows. First, he notes that operation B only needs the ID of the user, which we already have. So since we don't actually need the user to be loaded first, we can fetch it in parallel, collapsing the waterfall. We can also bring operations D and G forward for similar reasons. Collapsing the waterfall like this allows the request to complete faster, giving users a better experience. But to do this, we've had to use look-ahead to summon this knowledge, this future knowledge, into our parent resolver. And this typically involves looking through abstract syntax trees and manually correlating them with your business logic. It's error-prone, it's repetitive, and it's the kind of thing that future you will curse when it comes time to refactor this code in 6 months' time. If taken too far, an evolving system that uses look-ahead can exhibit bizarre and hard-to-exorcise issues, believe you me. Back to GraphFast. If we study the plan diagram for our request, we might see the same opportunity for optimization. The B step gets the ID from the A steps result. But we know that this will always be the same as the input into the A step. So really, we'd rather get it from there. Now, this A step will have been generated by a call to load1, like this. And if we add this argument, that will tell load1 that children who request the ID field should instead be given the input, because we know that it's going to give the same value. If we apply this approach to the entire operation, then we allow more steps to exist in parallel, resulting in the same waterfall as Andy's version 4 optimized execution. And all it took was adding a single argument. No arcane knowledge necessary. So, just using GraphFast's built-in steps can give us level 4 of Andy's optimization as our baseline in GraphFast execution, which is excellent. But I've only shown you the very basics of the system so far. So let's jolly well step it up a level and unlock new heights of efficiency. The real power of GraphFast comes when you build your own step classes, which isn't much harder than building a data loader. Step classes are the way that you describe your business logic to GraphFast. They can expose custom methods for developer ergonomics, and because those methods are called at planning time, they can automatically help us to solve these overfetching and underfetching issues as we saw in the waterfall compression just now. But the real magic happens when you add the optional lifecycle methods. The GraphFast system will go through each step in the plan diagram and, via the lifecycle methods, give it a chance to deduplicate and optimize itself by collaborating with the other steps. This enables the work that needs to be done to be restructured, to be combined and reallocated in the most efficient way, whilst remaining spec compliant. Let's take a look at two of these methods now. Deduplication allows us to spot steps in our plan diagram that are equivalent to other steps and to eliminate one, replacing it, substituting it for its siblings. This means more efficient planning and more efficient execution. And it's important to note that the deduplication that we do here is on the steps, so it allows much greater possibilities than just deduplicating aliased fields, for example. Optimize is the most powerful lifecycle method. Let's look at an example to get us started. Imagine that our plan diagram has a step that represents a Stripe customer. And below that, we get the customer's ID, and we use that to look up the subscriptions for that customer also from Stripe. By using dedicated step classes for these tasks, when it comes time for the Stripe subscription step to optimize itself, it can spot that its grandparent is a Stripe customer step, and it can ask it to also get that customer's subscriptions at the same time using the expand capability that's built into Stripe's API. Then it knows it's not going to be needed anymore, so it can replace itself with a step that just accesses this new subscription data. So, GraphFast enables us to solve the problems of over and underfetching, but even people who've already solved these problems can still benefit from GraphFast's planning system. Now, important, do not worry about the code on this next slide. Again, we only care about the shape. Some of you may be familiar with one of my projects, PostGraphile. In version 4, we eliminated over and underfetching from the database by using an extreme form of lookahead to build a single SQL query to get all of the required data. This resulted in significant performance gains over traditional approaches. Now, keep an eye on that right-hand side. PostGraphile version 5 is a ground-up rewrite on top of this new GraphFast planning engine. And this is the SQL query that it issues for the same GraphQL request. This SQL query is 1/4 of the size, and it executes in just half the time, even though the previous query was very carefully optimized over a period of 5 years. Unlike the previous query, the structure of this SQL query doesn't reflect the structure of the GraphQL request. That's because GraphFast can allow the steps to rearrange themselves in any way that they like, and GraphFast will then take care of making sure that we still output the expected GraphQL response. And you can use this with any system where you can declare what you need up front. So, various REST APIs, all GraphQL APIs, most ORMs, any SQL, and probably even your own business logic. Now, this planning may make you think of the various GraphQL gateways that use specialized planning to figure out how to split the incoming operation across the underlying GraphQL services and then stitch the responses back together again. Now, if you need that, use a GraphQL gateway. Their capabilities are honed for this purpose. GraphFast is not specialized. It's a general purpose planning and execution engine. But executing GraphQL efficiently is a widespread desire. So there may be many techniques that you may have seen across the GraphQL ecosystem that try to address it. There's look ahead, which we just saw. There's transpilation, where you take a GraphQL query and you convert it to another language, such as SQL, and execute it there. That's quite specialized. There's projections, which is a kind of hybrid approach between traditional execution and transpilation. And there's also the concept of delegation that allows you to extract small parts of your incoming GraphQL request and issue just those as a new request to a downstream service. From talking to people over the last couple of days, it seems there's even more ways that people have tried to solve this problem, often leading to their own in-house solutions. Now, all of these techniques involve looking through the abstract syntax tree of the GraphQL request. And in my opinion, anyone who's messing with the abstract syntax trees during GraphQL execution should use GraphFast instead. Developers using look-ahead, transpilation, projections, delegation, their own in-house query planning may find that GraphFast's planning system allows them to be more concise, more expressive, and to generate more optimal queries to their backends. Now, there are situations where GraphFast won't be better for you. For example, if you interpolate your queries rather than using variables, and your queries are pretty small, then the cost of planning may outweigh its benefits. But if you're using GraphQL for your own applications and for your own websites and mobile apps, and you're using the same few thousand queries time and time again, but with different variables, then the future of efficiency is here. Add general purpose query planning to your GraphQL schema. Planning that supports all forms of business logic. Planning that eliminates the N+1 problem by design. Plan resolvers that are ergonomic to write and yet lead to extremely efficient execution. And you can adopt it incrementally. Though GraphFast uses this plan resolver system, which is a completely independent execution model to resolvers, we support a resolver compatibility layer, which means that the vast majority of existing GraphQL.js schemas should already work with GraphFast. So, the first step in your GraphFast journey to efficiency starts with your existing schema. You then can move from traditional resolvers to plan resolvers on a field-by-field basis, and you can start by using the built-in steps and combining them into your own utility functions to make them easy to refactor later. Over time, you can move to using your own step classes, and you can use GraphFast's automatically generated plan diagrams to discover the opportunities for optimization, which you can then enact via those lifecycle methods. Many of you may know of Sean Grove, one of the people behind the OneGraph project that was acquired by Netlify a couple of years ago. Sean's been helping to test the early versions of GraphFast, and he says, GraphFast feels like the missing substrate in the GraphQL world. I couldn't have put it better myself, Sean. This missing piece in the GraphQL puzzle is why I've poured so much of my time and my heart into this project over the last 3 years. And I've just this morning released version 0.1 on GraphFast onto NPM under the extremely permissive MIT license. GraphFast already works, and some of my sponsors are already running it in production. You can try it out today. Just follow the guides or set up the mailing list, sign up to the mailing list at graphfast.org. I'll be further improving the documentation and writing more examples over the coming months. Now, this is where I ask for your help. There's still decisions to be made and edges to be smoothed before we can turn GraphFast into a specification that can be implemented in any GraphQL service in any language. If the potential of this technology is interesting to you, please consider joining the GraphFast working group and getting involved. We all deserve our future of easy, GraphQL execution efficiency. It may be of particular interest to programming languages that don't have a run loop. I'd like to take this opportunity to thank my sponsors who've supported me throughout this process whilst I've been building this new technology for the benefit of everyone. I'm a community-funded open source developer, so there's no way that I could have done it without the support of these people and companies. I am so grateful to them. If this technology has been at all interesting to you, please do try it out and get involved, or consider sponsoring me. And remember, don't do it half-assed, do it graph-assed. I look forward to talking to you all in the hallway, or on Discord, or Mastodon, or whatever he's calling it this week. Thank you. Are there any questions?
I didn't quite follow how your system knew that the API had an additional parameter behind the additional data. Was that by a life cycle that you is that a life cycle? Is that how you write that?
Yes, so the question was, how did the system understand that there was that expand capability in the Stripe API? And the answer is, you write your step classes and you add the lifecycle method that that talks amongst itself, amongst its own step classes, and they can communicate with each other to say how that works. So you describe that yourself.
Is it possible to do the query planning as an ahead-of-time compilation step, or must it be done at runtime?
The question was, can you do the query planning ahead of time, or does it have to be done at runtime? At the moment, it's at runtime, but there are plans to make it so that we can do it ahead of time. Basically, once we've done the optimized stage of the plan, the idea is that we should be able to export that as like a JSON object, and then you can read that back in from a cache, run a finalize method on all of your steps just to make sure that they are in whatever state they need to be, and then you're ready to go. So it should be able to do that. Yes?
Is there any plan to do more than just query, but also into mutation?
Is there any plan to do anything more than just query, but also mutations? Yes. GraphQL supports everything in the current draft of the GraphQL spec. It supports query, mutation, subscriptions. It even supports an earlier version of stream and defer. So all of this stuff that you do in GraphQL, you can do in GraphQL. Also polymorphism, everything that you can do according to the GraphQL spec, you can do with GraphQL. Yeah.
So in some of the backends, they have very good analytic functions, such as sum and count. Now, how do you, I mean, if you have a need to leverage that kind of power, right? If you only need to get the sum, you need to read all the rows out or documents out in order from the sum in your server. Wouldn't it be better to push that function down?
So the question was, if you want to do aggregate functionality such as summing, wouldn't it be more sensible to push this logic down into your data store rather than pulling all the documents out and doing it yourself? And absolutely, that's what GraphQL enables. If we look at the, I mean, it's ridiculously tiny code, but if we look at the code that we saw in the database queries from the PostGraphile example, you can put aggregate expressions in this, and that would be enabled by your own GraphQL step classes. So your classes, we're not requiring that you pull data into the GraphQL layer to do this. Your classes describe what they're going to do as your arbitrary business logic. So if they want to do a sum, they can just do a sum themselves, and they handle how that happens. So like you would do, if you needed to do the sum in a data loader, for example, you might well just have a data loader that goes and does a sum operation in your database. You do the same thing with GraphQL. Planner is over, yeah.
Plan, yeah. Your GraphQL plan changes how it actually operates or what you put in.
So the question was, if we're going to standardize this via like a JSON that we write to storage somewhere and then we read that back, what happens when things change? And I'd say just plan again. Just run the planning again. Build a new JSON, whatever you need to do now.
One question. Before GraphQL, we analyzed the AST of GraphQL to analyze what we should do to optimize the queries. Now we analyze the AST of the query plan to analyze how to optimize it. Or is there some way that the optimizer helps us that we don't have to like visit the tree and then figure out that we need this sub collection or whatever? Or is the optimize step just there's the context, do it yourself?
This is a really, really critical point, so thank you for raising this. So the question was, if you, previously we had to browse through the AST of the GraphQL query, now we're just browsing through the tree of steps, right? Is that what we're doing? The answer is no, that's not what we're doing. All the steps are actually doing is communicating with their parent step. They don't need to worry about the tree in general. They will have, or they can add specific optimizations, but you generally, in fact, it is designed so that you would not manipulate the query plan as a whole. You always do your modifications locally to you, and that is critical to ensure that we still conform to the requirements of the GraphQL specification. So there is no tree walking, there's nothing like that. It's literally just look at my own steps dependencies, see what they're doing. Maybe if you know that it's an access step, see what its parent is, and normally that's about as far as it goes. You can do more, but...
Quick follow-up. Is there only one pass through the tree, or can we do this iteratively?
We're getting deep into the weeds here. Is there just one pass through the tree, or can we do it iteratively? The answer is, for each step, for each lifecycle method, it's different, and the order in which we do it through the tree is different, and this is, again, based on the requirements of the GraphQL spec. But for optimize, by default, every step only gets optimized once because it needs to know what its parents are. So you start at the leaves, and you optimize backwards towards the root so that everyone always still knows what their parent is. For specifically highly optimized step classes, they can opt into optimizing more than once, and that means that their parent might be something else. Like their parent might have been that Stripe subscription step at one point, but now it's just an access step. So long as they can handle that, they can opt into the ability to optimize multiple times. But typically, I would only expect that to be used for like the built-in core steps like access and map and things like that. Thank you so much, everyone.